we'll get started. So in the previous lecture, we were talking about multi-armed bandits. So what was the setting? We had a family of n alternative bandits. We have IID rewards that are independent of other bandit rewards. And then what else we had? We wanted to minimize. The goal was find policies mu 0, mu1, so on, that minimizes regret, which was defined as m star minus mk, expected value of TKT. TKT is number of times arm K was pulled, or the action was to pull the kth arm. So number of times arm K was pulled until from 0 to t minus 1. Okay, so some paper will start the time from 1, some papers will start the time from 0. So I'm just writing it from 0 to t minus 1. M star is the best arm, which we do not know, which is what's the average reward coming out of the best arm. Mk is the expected value of the reward coming out of the kth arm. Okay, that was our problem setting. I'm just reproducing what we did in the previous lecture. The other thing we talked about was a result that regret of mu t should be order of log t. And in this case, the log is base e, so it's natural log. And the idea is that regret of mu t is always greater than equal to log t, some order of log t, and you can create policies mu which is less than equal to the constant times log t plus some small error that can be made arbitrarily small. So that's why I'm writing it as approximately equal to order of log t. So we want to find policies mu such that the regret is order of log t. How will I get this regret order of log t? So let's say, okay, let's get to it in a bit. Okay, any questions so far on this setting? These are the stuff we did in the previous lecture. Yes.
In the homework, you use m hat.
Yes.
So m hat is just the sum.
I'll introduce it right now. Yeah, in some time. Yeah. It's the empirical expectation of the reward. Any questions so far?
I have a question.
Yes.
Can policies mu is equal to mu 0 to
all the way up to mu infinity.
Okay.
Yeah. Ideally you want to be using this multi-arm bandit all the way until infinity. You want to optimize the average cost, so you want to get to a point where you're pulling the best arm all the time. But naturally, in the interim, until you learn that particular policy, you want to be minimizing the regret. So regret is, if you knew everything, what would you have done? Minus, now that you don't know stuff, what are you doing? And what's the difference between the two rewards? So in some sense, minimizing the regret means that you are optimizing the transient performance of your learning algorithm. You ideally want to not pay too much price to learn what the system is, what the optimal performance for you is going to look like. So a bunch of questions that arises. How do I get regret? How do I come up with policies that would give me a regret that is order of log of t? And I think the answer lies in looking at this particular expression. So what does this say? So there is one arm which is m star, which is equal to m star. So you want to pull it more often. The other arms that are suboptimal, so mk is strictly less than m star, you want to be pulling it log t number of times, right? In a time horizon capital T. So if capital T was 100, what is log, natural log of 100? Can someone calculate it? What is log of 100? So T equals to 100. This is natural log. I'm assuming it should be 5 or something. 5 or what? 5? About 5. So let's say n is equal to 3. We have Kroger, Giant Eagle, and Whole Foods. N equals to 3. I'm going to look at a 100-day horizon. Okay, so I'm going to be going to some grocery store every day over a 100-day period. I can go to the non-optimal grocery store 5 times in that 100-day period. And I want to go to the optimal grocery store 90 times in that particular period. Okay, does that make sense? That's how we'll get the log of t regret by picking an appropriate policy. Okay, so all right, so now let's go to day 0. Okay, day 0, you landed in Columbus, and now you're hungry, you need to figure out which grocery store you want to go to. And let's say you came up with for some reason you went to Kroger on day 1. And so this is arm 1, arm 2, arm 3. So on day 1, your grocery bill was $10. So T equals to 1. T equals to 2. You went to arm 2. Your grocery bill was $20. T equals to 3. $15. Okay, so now you have done the exploration once. You've gone to all 3 different places that were available in the city of Columbus. T equals to 4, what are you going to do? T equals to 4. Just pick arm 1. Your grocery bill was $11. T equals to 5. What are you going to do? Let's say we go to arm 2 again. $15. T equals to 6. Okay, so now we are in an interesting setting. Which one would you go? Yeah.
The regret should be mu star or mu?
Not mu star. You can never figure out what the optimal policy is. The optimal policy is always to pick the arm.
I see that the O.
Okay.
This should be.
So what did we prove in the previous lecture? Regret of mu of t is greater than equal to O log t. And regret, there exists mu such that regret of mu of t is less than equal to O log t plus epsilon, where epsilon can be made arbitrarily small. Okay, so the first one is saying that for all mu, this is for all mu. So you get a lower bound on the regret, and then you say that there is a mu that has the same order plus epsilon, where epsilon can be made very small by picking a large enough horizon. Okay, So now t equals to 6, what are you going to do? Okay, let's say you went ahead with ARM3 and you get $12. Okay, and so on. We'll continue doing this on a daily basis, and we are going to accrue certain amount of certain bill. Then we are going to compute m hat of k at time t, which is the summation of reward that you get at time k, such that the arm was pulled, the kth arm was pulled, t equals 0 to, oh, I use t here. Let's call it capital T. No, I don't like this. I'll use J for an intermediate time. Okay, so at time t, I compute the empirical expectation of all the rewards that I've gotten from the kth arm. And let's say my m hat 1 at time 50 was $10.65. M hat 2 at time 50 was $12. M hat 3 at time 50 was $11.5.
M hat without averaging.
Oh, there is an averaging. Yes, there is an averaging. Thank you. TKT. Yeah, there is an averaging. So I looked at my history of how much money I spent on ARM 1 or how much reward I got at ARM 1, and then I picked I computed the average. I did the same thing for ARM 2. I did the same thing for ARM 3. Where would you want to go at time t equals to 50? So this is your 50th day in Columbus, and you need to figure out where. By the way, I'm using reward, but I'm talking about cost, so I guess think of it as a reward. I don't know. Well, okay, let's think about it from a cost perspective. It's much easier to understand this example with a cost. Okay, so this is the cost that you're paying in Kroger. This is the cost you're paying at Whole Foods. This is the cost you're paying at Giant Eagle. Where will you go on 50th day? Yes. Oh, ARM 1?
ARM 1.
Okay. Okay, so you want to pick this one. How are you sure that ARM 2 and ARM 3 are suboptimal? You're not sure, right? So then why are you?
This is the best thus far.
Best thus far. Okay, so this is the best thus far. But he's still not very sure if ARM 2 and ARM 3 are going to be optimal or not. Okay, so on 50th day, he has maybe a few data points from ARM 2, few data points from ARM 3, few data points from ARM 1. He's thinking that ARM 1 seems to be the optimal. It has the cheapest groceries for the quality that he's looking for. But ARM 2 and ARM 3 is not too far off. So maybe we need to go to ARM 2. We need to go to 2 or 3. Okay. Anybody else has any other thoughts? Where would you go?
Maybe we can run p-tests.
Okay. We'll do that in the next class, but not this class. Okay. All right. So here, let's say I have T150 is 40, T250 is 5, T350 is 5. So you have gone 5 times to Giant Eagle, you have gone 5 times to Whole Foods, you have gone 40 times to Kroger. So it seems to me that you have not really explored Whole Foods very well, and you have not really explored giant eagle very well. What if on those specific days, the 5 days that you went to, there was a snowstorm, so the price of food was expensive, and now Whole Foods might be running a promotion and the price might be cheaper? How do you know, right? We don't know. Lots of things that goes on which influences the cost of the groceries. Okay, so somehow I need to say that maybe you don't want to go here, maybe you want to go here. Who knows? Maybe you get cheaper groceries at Whole Foods. Even though the evidence says that this one is cheapest, but I want you to go here. Okay, so how do I incentivize you to pick arm 2 rather than picking arm 1? What can I do to incentivize you to explore? Go to places that seem suboptimal based on the data that you have so far, but who knows, it may be optimal. You just don't know, right? Okay, so based on the percentage that you have visited, what do you want to do? Add an additional term as a penalty. Okay, perfect. Awesome. So what his idea is that based on how many times I have been there, I'm going to add a penalty term to places that I've explored more, and I'm going to not add the penalty to places that I've explored less. However, the penalty that you are going to add for places that you have explored less, you want to make sure that if it is the wrong arm, you only go there log t times, okay, and not more than that. So this was the original idea. This is the policy that achieves this log t plus epsilon regret. Okay, and then there were lots of work, but the original policy from 1985 paper was very complicated. So if you imagine when you search on Google, the layout has to be computed in a few microseconds. Okay, so they need to populate the layout and they need to create the entire thing, and that has to be done in a few milliseconds or microseconds. So you cannot have extremely complicated muse which takes into account the entire history of rewards that you have seen and figures out what action you need to take, because there are computational limits. You want to be able to serve the request, the user's request, in a matter of a few milliseconds. So there was this whole search for simpler policies, simpler muse that are not very complicated, which can give you log t performance. Maybe the constants would be bigger, and that's okay. I don't worry too much about the constants, but I still want the log t performance, because the t in the case of Google could be 1 billion, because there are 1 billion people using Google on a day-to-day basis, or t for Netflix could be 1 million, because 1 million people are watching Netflix on a day-to-day basis. So I still want the order of log t, or log t square, but I still want to retain this log t term or log t square term. So therefore, this tk of t for non-optimal arm should be log t or log t square. All right, so let's go back to the, okay, so well, good. Okay, so I want to take a small detour right now. So that's one method to do it. Is there any other method? So one method that we discussed was I'm going to add a penalty term depending on how many times I have visited that particular location. But are there any other things that we could do? Yes. Wonderful. So you are going to pick these numbers, and then you will construct a probability distribution, and then you're going to pick the arm according to that probability distribution. Perfect. That's also a valid algorithm. But let's think about it in a different manner. So right now, what we have used is the past data to compute the empirical estimate, and then we figured out, okay, where should we be going based on certain criteria that we've discussed. One more option that somebody suggested in the previous lecture was, we'll ask our friend, okay? And the friend is going to suggest that let's go to whatever X place, and you will get the best prices there. let's try to build on that particular thought process. So what exactly is experience of your friend? What do you call experience of your friend?
The penalty,
Sorry?
it's like a penalty.
Not a penalty, okay. No, experience of a friend prior, okay. So were you saying the same thing? Okay. So experience of a friend serves as a prior. Okay, so what is the prior? It's the initial belief of what exactly would be the best place for you. So if somebody suggested Kroger, so you asked one friend, he suggested Kroger, you asked second friend, he suggested Whole Foods, and you asked the third friend and she suggested Giant Eagle. So now you have one third, one third, one third prior. So one third is the probability that Kroger is the best place, one third is the probability that Whole Foods is the best place, and so on. So now that you have the prior and you're going through this learning process, what you can do is update your posterior based on the information that you are gathering. So you have prior, you get data, and then you get posterior, and then you get data, and then you get the second posterior, and you can continue to go on and on. And hopefully the posterior is going to concentrate on one specific arm eventually and say that that particular arm is the optimal arm. So this sort of algorithm is known as, this class of approach is known as frequentist approach. To bandit, and this one is known as Bayesian approach. For bandits. So when you look at the literature, many papers in the early days were not making the distinction between frequentist and Bayesian, but later papers made that distinction. So you'll have two classes of papers on bandit algorithms. One is a frequentist approach to bandit. The other one would be the Bayesian approach for bandit. The idea in the Bayesian approach is you will have a prior distribution over what is good and what is bad, what is the best arm and what is not the best arm. Based on the data, you will update the distribution of the rewards. You will get the posterior for the reward distribution, and based on that, you will pull the arm, appropriate arm, and then you will get more data, and then you will update the posterior, and so on and so forth. The benefits of the frequentist approach is no model for reward needed. All you need for frequentist approach to work is to understand the support, to know what the support of the reward distribution is, which in many cases you typically know. So in the case of going to Kroger every day and buying food, at the most, the cost that you are going to pay would be between 0 and 100. Okay, it's not like you're going to pay $1 million to Kroger to buy, I don't know, a bunch of eggs. Although that might have happened a few months back, but it's not the case anymore. We have enough eggs, right? So the support is all that you need to know what the reward support looks like, but you don't need to have complicated models on the prior and distribution and so on. The other benefit is it uses empirical estimates, moment to compute policy. Okay, so the policy is basically using empirical mean and moment information, which in most cases is extremely easy to write a code for that. Okay. So you would typically have two numbers. One is M1 and T1. And when you get the new information, you can immediately update the new M hat based on the new information that you are getting. So it's extremely lightweight execution of the policy. This one need a model for reward distribution and need to compute posterior distribution. Okay, so now in the case of Bayesian approach, you need to have a model for reward distribution. So the reward is distributed in according to a Gaussian distribution or sub-Gaussian distribution or uniform 0, 1 or something like that. So you need to have some prior on the reward distribution. So you need a lot more knowledge about the reward, and then you need to invest a lot of effort into computing the posterior distribution in the case of Bayesian approach. You have a question? Yeah.
So does that mean conjugate prior?
Yes, exactly. Okay, so in the case of, so what Phil was talking about is there is a subclass of distributions for which the computation of posterior distribution is very easy. That whole class is known as conjugate priors, and you can go to Wikipedia and look at a whole bunch of conjugate prior distributions. So most of the Bayesian approach essentially ends up using the conjugate prior sort of model because that's much easier to work with. And it has some nice properties and nice regret bounds and all that stuff. So you will see like both kinds of papers, frequentist papers, very little assumptions on the reward model, and uses empirical mean and stuff to compute the policy. And the Bayesian approach would be to use conjugate priors to figure out what is the next best arm to pick. Any questions so far on what we've done? Okay. You can start figuring out which is the best grocery store to go to tomorrow onwards. Okay. Today we'll talk about the algorithm. All right, so I'm going to erase this side.
I just have a quick question.
Yes.
For the frequency approach, okay, so
Yeah.
as we have more rewards history,
Correct.
Longer history of rewards,
Right.
so the current best option or action may change. So if someone, for example, action 1 and action 2 are very close, they're distributed, if they are really close, and
That's
the
right.
noise is very large.
Correct.
So the
Yes.
optimal action may change very frequently.
Absolutely. And there the learning horizon will be very long. Okay. So again, so that's why I talk about different applications, because you understand the horizon length only if you understand the application. So if 1 billion people are using Google every day, you can collect 1 billion samples of different arms in a day. On the other hand, Netflix can only collect 1 million because it's not like 1 billion people are going on Netflix and watching Netflix every day. But if you are New York Times, you might only collect 40,000 samples in a day. And if you are a vehicle manufacturer, you probably can only do 3 or 4 testings a day. So you can only have 3 or 4 samples of. So then this whole multi-arm bandit thing will not work for vehicle manufacturers, right? But it might work for Google and Facebook and Netflix and so on. And it may or may not work for New York Times. Okay. Yeah.
So you still need to choose a penalty.
Yes.
Right, but that is considered easier.
Much easier.
computationally, and
Yes, that's right.
Like you
So
just come up with something that
Correct.
satisfies.
That's right.
the bound.
That's right. All right. So I'm going to talk about. So a lot of work happened between 1990s, 1985 to 2000, and a lot of those policies were somewhat complicated. But it was important. Those were important papers, but that led to the first very efficient algorithm by our Bianchi Fisher, 2001. It's called the UCB algorithm. Now, of course, the original UCB algorithm was designed here in 1985, and there were a bunch of papers written on UCB type algorithms. But for what it's worth, nowadays, whenever somebody says UCB algorithm, they are actually referring to this algorithm, not this algorithm or this algorithm. So the UCB algorithm, the rewards are in 0, 1. The index of kth arm at time capital T is m at kt plus square root 2 log t over tkt. And then mu t it is argmax k index k. So remember, we were talking about index policy, so we compute some index for every arm, and then we pick the arm with the maximum index. So you first construct the index using the empirical mean estimate, and then this is the penalty term. So let's think about the penalty term. So log t is a function of the current time. So this is 50, log 50. But this one is a function of for how many times you have actually pulled that particular arm. Okay. So it can be 40, or it can be 5, or it can be 5, but log t is log 50. So that's same for every arm. And here the regret is O log t. O log t plus constant. And by the way, most of the people ignore the constant because typically t is very large. T is of the order of 1 million or so. So the constants don't really matter because constants are small. But certainly the constants that appear in the O log t may be pretty bad in comparison to the constants that are here. But this algorithm is close to the optimal, but very complicated. How much time do you think you will take to execute this particular algorithm? Maybe a few microseconds, nanoseconds, right? So in a nanosecond, or maybe in a couple of microseconds, you can actually compute the index for all possible k arms. So your n, in the case of Netflix, how many movies they have? 5,000 or whatever, right? Something in that particular order. So if they have 5,000 movies, you need to compute this 5,000 indices at every point of time, and in a matter of a few microseconds, you will be able to compute all those 5,000 indices, figure out what the best recommendation for the movie is, and you can serve that to the user. And the regret is going to be O log t in that case. Yes?
So this constant is a constant with respect to t,
Yes.
but this epsilon vanishes with t. Is that right?
This epsilon would vanish with t, but then you need to know this capital T upfront. You need to know how long that horizon is going to be. Any other question? Okay. Second one that I have is from the book on multi-arm bandit. So the index here is this also reward is between 0 and 1. For every arm, the reward is between 0 and 1. I do want to make a comment. So remember, in order to come up with this regret expression, the authors, Lai and Robbins, they assumed a parametric model for the reward distribution. But here I'm not assuming any parametric model for the reward distribution. So the rewards are, it can be any distribution as long as the support is between 0 and 1. So for instance, you could have one particular one arm that is giving you 0 with some probability and the other and 1 with some other probability. In the other hand, the other arm could be uniform 0 1. Okay, both of them are valid in this particular setting because we're not assuming a parametric model for the reward distribution. This one does assume a parametric model for the reward distribution, so something to keep in mind. Yes.
Why does the reward have to be bounded?
Yes, very good question. So why does the reward needs to be bounded? It has to do something with the proof technique that they are using to prove the regret bounds. Let me digress a little bit. In order to prove these regrets, there are only two ingredients that you need. The first ingredient is Hovding inequality. Or Chernoff-Hovding bound, or some sort of concentration inequality, which says that the probability m hat kt is greater than equal to mk plus epsilon is less than equal to some delta epsilon. And and a function of tkt. Okay, so how many samples were used to compute this particular m hat? So Hovding inequality in particular, the original Hovding inequality required bounded support. So the easiest bounded support is 0, 1. Okay, you can of course have any other bounds of the support. You can have a comma b, but then those a and b will appear somewhere in the regret bound. So nobody wants to carry a and b. So the first requirement is the Hovding inequality, which requires bounded support for the underlying random variable. But then later on, people have proved Hovding inequality for, let's say, sub-Gaussian random variables and for other classes of random variables. So therefore, you could sort of extend this restriction to sub-Gaussian random variables, and you would get some bound for the regret. It need not be the same bound, but some other bound for the regret. The second ingredient, in order to prove this regret bound, is the following identity. So let's say a is less than equal to b, and x and y are two random variables. Then the probability that x is less than equal to y is less than equal to probability x less than equal to b plus probability y greater than a. So Hovding inequality plus this particular identity and 7 pages of bookkeeping gets you to the regret bound. Okay. And then reviewers have to do all that 7 pages of bookkeeping, right? So I'm assuming many of you here are reviewers of papers. So yeah, a lot of trees were cut in order to compute these regret bounds for different penalty terms that were added to the empirical mean. Yes.
What is specifically significant about this regret in this Lattimore and
So this is these constants and everything is better than this particular constants here in this particular algorithm. Okay. The other thing I wanted to note here, imagine, so this is mk less than m star. So let's say m star is 0.51 and mk is 0.49. Okay, so mk, the second best arm, is marginally lower than m star. Then this particular term is going to blow up, right? Because this particular difference is small. So you will have a pretty large constant here multiplied to log t. And that's because you could have two arms that are arbitrarily close to each other in terms of their mean reward. But that's okay, because in a larger scheme of things, you're essentially pulling the two arms that are close to each other in terms of mean reward. So you're not pulling the best arm, but the second best arm is not too far off from the best arm. So I think it's okay. Yeah.
So I guess like that seems to contradict the equation. So like you're saying in practice it's okay, but the equation is blowing up. So
That's right.
what is that just says that this.
So this is the regret. Yeah. So this is the regret bound, right? So this is an upper bound. Yeah. So the upper bound could be really bad, but it doesn't matter much. Yeah.
I have a question.
Yeah.
So we are talking about the regret for the previous analysis.
Yes.
This class.
Yes.
Multi-armed bandit. But for general MDP and IL, regret seems to be less discussed.
That's right.
So why?
It's
It can be used. I think theoretically it can be used, right?
No, I mean, there have been many papers written on regret bounds for MDPs as well. We will talk about UCRL2 algorithm maybe next week on Tuesday. But the problem is, okay, so again, going off track, if a PhD student has to compute these regret bounds, they have to be fairly mathematically sophisticated. Learning Hovding inequality and this identity itself is somewhat difficult. So you can solve this class of problems very easily, But if you have to solve the MDP problem using regret bounds, it becomes order of magnitude more difficult, because now you have a transition kernel, you have a reward that's a function of state and action. The state and actions have correlations across time. So now your reward function has correlations across time, the reward samples that you are getting. So the amount of bookkeeping you have to do is incredibly higher, and you can't get a PhD by just doing bookkeeping of 100 pages rather than like if 7 pages is going to get you a PhD, why would you do 100 pages of bookkeeping, right? So that's I mean, that's not the correct view, but it gives you an approximate view of why this field blew up so much, because it's much easier to do this kind of work than to do it for actual MDPs. But that is not to say that people haven't done that, but they have been mostly postdocs, not PhD students. So, but yeah, there is a lot of work on UCRL, UCRL2, and many other algorithms. It's just that the proofs are much more complicated, and yeah, you're no longer in the IID setting, so the Hovding inequality doesn't apply, and then you have to have mixing processes, and you have to have diameters, and so on and so forth. So we'll talk about that in the next class.
Continuous action space.
Yeah.
Has there an extension for this regret?
Yes, we'll talk about kernelized bandit at some point of time. So that's for continuous action setting. Yeah. So the continuous action bandit is an important problem, and I'll give you a very specific application. So let's say you are a mining person, and you want to you have drilled a hole here, and you have figured out that 2% of this soil is copper, and you need to figure out, okay, how much copper is there in this area. In order to do that, you need to drill holes multiple places. Each hole drilling is going to cost you a lot of money and a lot of time. So you need to figure out where to drill the next hole. Should it be 10 meters away? Should it be 100 meters away? Should it be 1,000 meters away? Right? So you are in a 2D space, and you need to figure out how many holes to drill in order to estimate, come up with a good estimate of, that's your reward, come up with a good estimate of how much copper is there in this mine, or how much oil is there in this well, or how much whatever lithium, that's the hot topic right now, how much lithium is there in this area. And so those are continuous action bandit, where you have drilled 5 holes, and now you need to figure out where the 6th hole should be drilled, and that's a continuous space problem. But the action space there is R2, because it's a 2-dimensional grid. Okay. Third algorithm is KL UCB. I don't know whether I want to do KL UCB or. So you define the one minus. I think the regret here is also log t. Okay, so in the KL UCB, you come up with the KL divergence of two random variables, one with distribution. So Bernoulli is 0-1 distribution. It takes 1 with probability p and 0 with probability 1 minus p. So you take the KL divergence of the two Bernoulli distributions, and then you figure out the index by maximizing for all q this KL divergence being less than equal to some threshold. Okay, and then people have studied this and have identified that the regret is also log t. Yes.
The reward is also.
Reward is also between 0 and 1.
And then this regret, this is an upper bound.
This is, yes, all regrets are upper bounds.
And does this have a plus epsilon?
It does have all those constants and everything, but again, because t is very large, people tend to ignore those constants. But you can go to the actual paper and you can figure out what those constants are. They've computed it.
But I guess, I mean, there's a distinction between these two cases. One is constant, the other is not constant. I'm asking, which is this?
Yeah, so there is a constant. Yeah. There are constants in all the regret bounds, but yeah, people. So whenever colloquially people say that my regret bound is order of log t, so they don't talk about the constant because everybody tends to ignore constants in colloquial thing. But
So, sorry, this one has no constant.
this one,
Yeah, no.
yeah, it has a constant. In the previous lecture, I had mentioned.
But there's like multiplicative constants and then there's this additive. And you made a point, the difference between this and this is that the additive constant on the right is fixed with p.
Yes, it's fixed
whereas
with
this
t.
epsilon decays with
It decays with this capital T.
t. Right, so I'm asking in this case, which of these is,
So all of these constants are fixed constants. In all these algorithms, the constants are fixed. It doesn't depend on capital T. Yeah. And by the way, again, when I'm saying this is order of log T, this could also mean C1 of log T plus C2 of log T. But again, this term is dominated by this term for T sufficiently large. So again, people say order of log T when you go into the proof, you will see that there is C1 times log T plus C2 times log T. And you could even have a square or something somewhere. But again, these terms are smaller, so people tend to just keep this term. And again, constants, again, because capital T is very large, so constants are very small in comparison to capital T. So then,
is the constant is really small with respect to the C2 term, right? Because that term grows with C.
yes,
And the constant doesn't. So
constant doesn't.
the constant is even less important than this other term.
Exactly. So that's why people write the dominating term here. So some algorithms would be log T square, right? Because that's the most dominant term and the other terms are sort of hidden.
Actually, this is the definition of infinite.
That is the definition of
Infinite.
infimum,
Infinite, yeah. The limit is infinite.
lim inf.
Yeah,
Yeah.
If.
Okay.
It's definition of if.
What is the definition? I didn't understand your point.
Oh, wow. Okay.
I think
Okay,
it's saying
maybe we
this is
can-
the definition of one.
Right. That's right. Yeah. Yeah. So this one was lim inf, and there was a constant which is the difference over the KL divergence of the two distributions. Yeah. Any other question? By the way, this book is available online. It's on Carmen, so you can download this book. It's only about multi-armed bandit, So you'll find a whole bunch of algorithms and the regret bounds in that particular book with exact constants and exact formula. So this book is available online for free for anyone to download and use it. There is a Boltzmann exploration. So this is where the probability at time t to pick k arm is given by exponential eta t m hat kt over summation over j this is the probability of picking arm k at time t. Tau is given by 32 e log t over delta square. So there are, let me write it as m so there are two arms here, so n equals to 2, and this is delta square. Delta equals to m star minus the suboptimal m, and eta t is given by 1 t less than equal to tau and log t delta square over delta t greater than tau. So I have two arms. I'm going to pick probability of picking arm k at time t. I'm going to compute that. This is known as Boltzmann exploration scheme. We saw an instance of this exploration scheme when we were talking about SARSA, one of the reinforcement learning algorithms. So it's the same Boltzmann exploration scheme. And delta here is m star, which is the optimal expected reward, minus the suboptimal expected reward. So that gives you delta. Because there are only two arms, so delta is just a constant. You pick a horizon tau based on how long the total horizon of your learning is going to be. So this capital T is supposed to be known upfront. So at time 0, you need to know how long you're going to run this algorithm. And so based on that, you pick the value of tau. You pick eta t equals to 1 until tau. And after tau, you start picking the eta t according to this particular schedule, and you use that eta t in order to compute the probability of picking arm k at time t. Okay. So in some sense, you need to know delta upfront. You need to know it at the very beginning. Very hard to satisfy in practice, but you know, if someone has given you this information upfront, then you can use this algorithm for exploration. And the last one that I want to talk about is Boltzmann-Gumbel exploration. So here the index is m hat kt plus and zkt is Gumbel distributed with the PDF minus C. So in this case, the regret is order of log square t plus constant. Yes.
So why, the reason that there is a log square t, is that because here you modify the signal moments of these
Yes.
distributions?
Yes. Yes. So so here because you are picking a Gumbel distribution. So the idea for Boltzmann-Gumbel actually came because Boltzmann exploration is equivalent to adding some sort of random variable to m hat kt. So the two would span the same sort of probability distribution. So then they said, okay, we are picking a specific class of random variables to add to m hat kt. So we are getting this sort of probability measure. Why not just pick some other probability measure and see, like some other random variable, and see what kind of regret we get? So that was the original idea, and they came up with Boltzmann-Gumbel exploration. I think this is, if I'm not mistaken, 2016 or 2017 paper. So the reason why I wanted to talk about Boltzmann-Gumbel is because it's a very interesting class of algorithm. So remember, before 2016, everybody was saying, I'm going to add a constant. So I'm going to look at m hat kt and I'm going to add something that depends on tkt, and that would be my exploration scheme. What these guys said is, let's keep this simple. Of course, tkt appears in the denominator, but just multiply it by a random variable, and that's going to induce some sort of probability distribution, and you will get certain regret. So in the assignment, I have asked you to simulate the Boltzmann-Gumbel exploration. Naturally, the regret is going to be higher for Boltzmann-Gumbel in comparison to others, but who knows, maybe you will find an application where Boltzmann-Gumbel seems to do better. All of these, remember, all of these regret bounds are upper bounds on the regret, expected regret. So you don't know in what situations it will be the best algorithm. So you have to try it out, and hopefully one of them will have lower regret, and then you can use that in production in whatever system you are trying to create. Yeah.
Sigma square is variance or some preset.
Some hyperparameter. Yeah. Like all learning algorithms, these algorithms also have hyperparameters, and you get to tune those hyperparameters depending on the application. Any other question? Okay. So if there are no further questions, I want to talk about the Bayesian approach to multi-arm bandit. So far, look at all of these algorithms. The idea is you compute the empirical mean, you add up something to the empirical mean, and you pick the one with the maximum index. You pull the arm with the maximum index, and some algorithms are more complex, some algorithms are less complex, some have higher regret, some have lower regret, and so on and so forth. In the Bayesian way, what you have to do is assume a parametric model of the reward function sorry, the reward distribution, and then we'll try to keep updating that parameter according to the observations that we have made. So let's try to understand the setting. So I have a parameter set theta. I have theta 1 to theta n. These are the n parameters for n arms. The reward R tk is distributed. I'm going to be using the density function, but so I'm using the density function, not quite a probability distribution, but RTK has PDF F theta k. This is the PDF. And as is the case, you're observing the information is, oh, you also have to have a prior, sorry. So you have a prior by on the parameters influencing the reward distribution. Yes.
So the different theta k's could have different priors individually.
Yes, they will have different priors. Yes.
I have a high-level idea of the Gumbel distribution. It can be used to sample from the sample the largest maximizer from the discrete distribution. This is the idea of the Gumbel distribution. So
yes.
I believe that the Boltzmann-Gumbel exploration difference between this and the last one is because that to maximize the index size, we can use to this Gumbel random variable, and then we can do the maximize index k. This is processed more smoothly because I think they are equivalent.
I wouldn't call it smoothly.
Yeah.
You know, because that
in terms of large k, in the case of large k, and this will be more efficient.
Could be. Yeah. I don't think this is something that they mentioned in the paper on Boltzmann-Gumbel. I would also say that Boltzmann-Gumbel doesn't appear in any of the books, but I still want to cover it in the class because I think it's an important class of algorithms. Like, it just gives you an idea about, yeah.
This study is just equivalent, and I just put it in my mind.
Maybe it is equivalent, but it's not written in the original paper that came out on Boltzmann-Gumbel, and not many people have studied this class of bandit algorithms. But I'm just saying it because, you know, I don't know where you will be working in the future, and this might just be much better than UCB algorithm or any of the other algorithms that we have studied. And you might even change the statistics of this particular random variable.
Oh,
right? Who knows? Yeah.
So, sorry, back since you changed what was written here with the priors. So are the theta k's independent of each other?
Theta k's are all independent of each other. Yeah. So this is a family of n alternative bandits. So all different arms are independent of each other in terms of how they are evolving. Okay. So I'm going to take a small detour and I'm going to talk about maximum likelihood estimate and maximum MAP. Okay. So what is the setting? So let's forget about this particular expressions for now, the setting that we are considering for now. So I have a parameter set theta. I have random variables. So the distribution is f of x theta. This is the PDF. I have samples x1 to xn. Well, n is already used. Let me use time t, xt. These are IID samples. And I want to compute. So what is the goal here? The goal is find theta using these samples. I have t IID samples coming from the PDF, and I want to find theta. How would you find theta in this setting? So let's say simple example. So I have a zero mean Gaussian random variable. I don't know the variance, so sigma square is unknown. I get t samples from that Gaussian distribution. I know that it is zero mean. I just don't know what the variance looks like. Now I want to compute the variance. How would you do that?
Moment estimation. And we can calculate the theoretical first order moment or the second order moment, and then we calculate the sample.
Okay, good. So you can use something like that. So you can use empirical estimate of the covariance, and that could be one way. Where did that thing come from? Where did that expression come from?
Yeah, we can calculate the give the theoretical mean.
Okay, let's assume. Okay, let's not assume that it is Gaussian. Let's assume it's some very complicated distribution. Let's say it's Gumbel distribution. Okay, let's say it's Gumbel distribution parameterized by theta, and I have some samples from it, and I want to figure out what that theta is. How would you do it? It's all IID. Yeah.
Data to maximize the likelihood of.
Yeah. So what is the likelihood? So I'll tell you what the origin of this likelihood is. So what's the distribution? What is the what's the probability distribution of observing x1 to xt? This is roughly proportional to f of x1 theta times f of x2 theta, f of xt theta. Right? That's the probability of observing x1 to xt. That's proportional to this particular multiplication. So one way to compute theta is, or I would say theta hat t, so that's an estimate of theta hat based on t samples of x, is to maximize f of x1 times theta multiplied by f of xt times theta, and this is theta over theta. So that's one way to do it. So in some sense, if I want to know the parameter, I'm going to multiply all of these functions together, and I'm going to maximize over theta. Alternatively, I can take the log of this, and I also get theta hat t equals to argmax of theta in theta summation I equals 1 to t log of f xt theta. And this is known as the log likelihood function. And the way to get theta is to maximize the log likelihood of the function. So that's one way to estimate the parameter if you don't have any prior on the parameter. And so if the parameter you are interested in is mean, then many a times just taking the average of the samples turns out to be the maximizing value there. Okay. Now we are in a different setting. Now, any questions on this? So this is the observed distribution PDF function of the t random variables, and I'm just trying to find theta that maximizes this particular product. Okay, and eventually there are lots of papers and books and all that stuff which says that theta hat t would eventually be a consistent estimator of theta under certain conditions as t goes to infinity. Now I'm in a different setting here. My different setting is I have a prior distribution on this parameter set. Okay. So what do I do then? So now I'm adding another thing here, that my pi 0 is the initial distribution on theta. Then what do we do?
We calculate the directing flow from the posterior and use the anti-MC or other important sampling or other rejection sampling to
Right.
proceed it, and we'll see which point it will converge.
Right. So good point. So what we will do in this particular case is we're not going to do MC and all that complicated thing. But all I want to do is compute the posterior on theta based on x1 to xt. Okay, so instead of computing theta exactly, what I'll get is a distribution over theta, but hopefully that distribution is much smaller in terms of variance based on all the observations that I've made, and eventually I'll converge to a value of theta that is most likely the theta that is giving out this x1 to xt samples. Okay, so I'll talk about this this second part, which is based on Bayes' theorem. How do you compute this value of theta? And then on the basis of that particular theory, we'll go back here, and what we will do is we'll try to estimate the posterior of the value of theta, and based on that we'll do some exploration in order to figure out what the policy is going to be, what this mu is going to be, and then on that basis we'll figure out what the regret bound of those class of algorithms look like. Perfect. So those of you who have not seen Bayes' theorem before, please go back and review the Bayes' theorem. I don't think we covered it in the class in the first lecture, but I could be wrong. But please do go back and look at Bayes' theorem and then be prepared for the next class. We'll meet on Tuesday, and we will. So next week, Thursday, there is no class because it's a break. Okay, so we don't have any class on Thursday. So Tuesday is the only class. We'll continue our discussion on the bandit algorithms, and if there is time, I'll talk about UCRL2 algorithm, which is applying this whole framework to the reinforcement learning setting where you have correlated states, not IID rewards, but you have rewards that are coming out of a Markov chain. Thank you so much. See you on Tuesday.